There can be some challenging normal distribution problems on an AP exam. Let's get comfortable with what we're talking about. If you have any random variable that's distributed normally with a certain mean and a certain standard deviation, we call that a non-standard normal distribution. But if your random variable is distributed normally and it happens to have a mean of 0 and a standard deviation of 1, we call that the standard normal distribution, and those are what the z-scores are. Now a z-score tells us how many standard deviations away we are from the mean. So if we take this situation where heights of adult women in America are distributed normally with a mean of 56 inches and a standard deviation of 2.5 inches, we have a normal distribution representing those heights. Now, the mean, it has a z-score of 0. So as far as its z-score, it is 0 standard deviations away from the mean. If we have a z-score of 1, it means we're 1 standard deviation away from the mean. And certainly if we add 1 standard deviation, 2.5 inches, to the mean height, we get 58.5 inches. So any woman who is 58.5 inches tall, they are 1 standard deviation away from the mean. If we have this height of 51 inches, that's 5 inches below the mean. That's 2 standard deviations below the mean. This is a z-score of -2. So the heights themselves would represent a non-standard normal distribution, but the z-scores associated with those heights would be considered standardized scores, because when you have a mean of 0, standard deviation of 1, it is the standard normal distribution. So the z table you get on your exam is a standard normal distribution table. We use that to handle problems like this. Let's suppose we're comparing two different populations and whose result was more extreme. Let's suppose we have Jimmy and he is a locksmith, and on average it takes him 110 seconds to break into a lock. Suppose you locked your car door or something, it takes him on average 110 seconds, and with a standard deviation of 15 seconds. Meanwhile, Mike Tyson, I don't know if you knew this or not, but he is now a clock cleaner, and so the time it takes him to clean your clock is about 260 seconds with a standard deviation of 20 seconds. By the way, with him, it's not the first punch you got to look out for, it's the second hand. That joke is funny because a clock has a second hand. Anyways, Jimmy, you want to see, well, how long does it take to jimmy the lock? Well, again, it's normal distribution with 110 seconds. So here's the deal. What we're doing here is we have, one day Jimmy says, whoa, this morning it took me 85 seconds to jimmy the lock. Tyson said it only took me 215 seconds to clean someone's clock. Well, who did a more extraordinary job in that particular situation? Well, what we can do is look at z-scores. If we look at Jimmy, here's his mean at 110 seconds. If we go 1 standard deviation this way, that takes us to 95 seconds, and 2 standard deviations this way takes us to 80 seconds. So you can see Jimmy's result was less than 2 standard deviations below the mean at 85 seconds. He's right here. We can find a z-score for that. We can take his 85 seconds minus the mean of his distribution divided by 15. That gives us a z-score of -1.667. So again, he's less than 2 standard deviations below the mean. So there's still a fairly significant percent of the time when he would expect to get a score that's less than that. When you look at Mike Tyson and what he did, well, his mean average is 260, and he's down here at 215 seconds. If we go 1 standard deviation this way, we're at 240. 2 standard deviations this way, we're at 220. And as you can see, he exceeded that. He is down here more than 2 standard deviations below the mean. If we find his z-score, it's x minus mu divided by sigma. His z-score, he's going to be -2.25 standard deviations below the mean. That's a more unusual result because there's a very small percentage of the time in a normal distribution when you get a result that's more than 2.25 standard deviations below the curve. So even though we have two different populations, it was Mike Tyson's cleaning somebody's clock in 215 seconds that was more exceptional than jimmying the lock in 85 seconds. We can use standardized scores, comparing the z-score, which is called a standardized score. We are using standardized scores to compare two different things from two different normal distributions. Wouldn't be appropriate to compare z-scores unless you have random variables that are normally distributed. But that's how that can work. We can say there are more standard deviations to the left than this individual. They win the battle of who did well. By the way, both these guys are selling stuff for the holidays for kids. Jimmy, of course, is selling, well, let's see, Tyson, he's selling clocks, obviously. All right, they're pretty spectacular. It'd be funny if you put a clock on a ring or in the ring, I don't know, whatever. But anyways, and then Jimmy, he's selling BB guns, but I can hear it now. You know, moms are going to be saying, you'll shoot your eye out, or he'll bite your ear off. So anyway, I don't know, you want to think twice before you order stuff for the kids. Lastly, here we go. Suppose the Michelin Man gets involved now, and how long does it take him to change a tire? Well, the time it takes him to change a tire, well, those times are normally distributed with the, what? We don't know. We don't know the mean, and we don't know the standard deviation. Hence, one of the more difficult mathematical problems in the AP exam. We know that it's a normal distribution, and we need some information so that we can ascertain how long it takes to change a tire. Well, let's suppose we know that for the Michelin Man, 2 minutes to change a tire is exceeded 80% of the time, and it takes him 160 seconds or more 5% of the time to change a tire. So we need to know what's the mean and what's the standard deviation. We're actually going to find the standard deviation first and use that to find the mean. Now here's why. The thing you want to go through in dealing with normal distributions is the z-score. It's that standardized score is the transition between a problem like this, where if you found the z-score, you could then go figure out the area below the curve. And here, if we can take the area below on the curve, use it to find a z-score, we're going to be able to transition that into what it takes to find the standard deviation and the mean. So that's what we're going to do. So the first things first, you got to draw a normal distribution so you can picture things. We know that 2 minutes, which is 120 seconds, is exceeded 80% of the time. That implies that there's 80% above this. But more important to us, because the inverse normal function and the z-table, the standardized normal table that you're given, is that all the areas are to the left of a particular z-score. So more important than the 80% above is the 20% below. Likewise, with the 160 seconds, it's true that that's exceeded 5% of the time, but more important to us is that the total area under the curve below the 160 is 95%. You can use the normal distribution table, but since you have a calculator, it's more efficient to go second distribution and use the inverse normal function on your calculator. And if you type in 0.2 for that, so again, if we go to the calculator, the inverse normal function is, we're going to clear this guy out. We're going to go second distribution, and then second distribution above vars. We're going to go to number 3, inverse normal, and we're going to type in the area. We want to find what z-score would trap 20% below in any normal distribution. So we type this information here, and then we paste it to the screen. If you have an older version of the calculator, you're going to type this in order. What area below the curve, and then the mean and the standard deviation. And there you go, negative 0.84. That implies that over here, if we go back to this, this situation, that this z-score down here is negative 0.84. Now what does that tell us? Very important. A z-score is how many standard deviations away from the mean we are. We are 0.84 standard deviations to the left of the mean. So the unknown mean at this point is sitting in the middle of the distribution, but the z-score tells us something very important. We now know that it was 0.84 standard deviations to get to here. Okay, then we go back and we do the same thing. We can do inverse normal of 0.95, want to trap 95% below, but the longer you've been in the course, the quicker you memorize this z-score, you'll find it to be 1.645. That means that the time by the Michelin Man to change a tire, if it's 160 seconds, is 1.645 standard deviations above the mean, because that's what a z-score tells us. really important to realize, what does the z-score tell us? Makes this problem much more doable. Understanding in the world of statistics is much more powerful than trying to memorize what to do in a situation. You can work through the problem if you understand it, and that's, in my opinion, the benefit of learning to be a statistician and be a problem solver. Okay, so here's the deal. How far is it from 120 to 160? Well, if we do 160 seconds minus 120 seconds, we know that this is a gap of 40 seconds. But we need to know the standard deviation. The z-score tells us how many standard deviations away from the mean we are. So what we know right now is this 0.84 is, this negative 0.84 means that at 120 seconds we are this many standard deviations to the left of the mean. Cha-ching. Now how about up here? How many standard deviations away from the mean are we right here? The answer? 1.645 standard deviations. That's what a z-score tells us. So if we say how far apart are these two scores, are these two z-scores, well, we would do 1.645 minus a negative 0.84. And if we subtract those, minus a negative, it's really you're adding it because it makes sense that we're 1.645 standard deviations and another 0.84 standard deviations apart. So this would be, what, 0.2485. 0.2485 standard deviations apart. So what we know is the difference between these two times is 40 seconds, and that equates to being 2.485 standard deviations apart. So the final step, well, actually the next to the last step in this process, is to say, well, then it must be true that 2.485 standard deviations, the distance apart in terms of z-scores, must be equivalent to 40 seconds, the distance apart in terms of seconds, time, units in this particular problem. So we just solve for sigma. We divide both sides by 2.485, and the answer that we get is going to be that the standard deviation is about 16.1 seconds. So we know the first part of the answer to our question. This is 16.1 seconds. All we need to know now is the mean. And hopefully you can do this logically. You can say, well, you know what? The mean is 1.645 standard deviations to the left of 160. So if we took 1.645 of those standard deviations, multiply them together, and subtracted from 160, we'd get the answer. That works for kids that are really comfortable with numbers and good with number sense. Let's do this instead. I'm going to go to a new screen, and here's what we're going to do. We're going to use the z-score formula, which has four things, z, x, mu, and sigma. We now, if we pick either one of these two times, we'll know 3 out of those 4 things. Like for this score, we'll know x is 160, z is 1.645, and we now know that our standard deviation is 16.1. We only have that 4th item, that 4th parameter or variable to solve for, so in the world of algebra, we're good. So we go to the next screen, and we're going to use the z-score formula. Z is equal to x minus mu divided by sigma. And we plug in what we know. The z-score for the time of 160 seconds was 1.645. We don't know the mean yet, but we know that the standard deviation is 16.1. Algebra time, we'll figure out what the mean is. Multiply both sides by 16.1, we get 2.5. So what do we get? I wrote 26. There we go. Thank you. 26.485. And that equals 160 minus the mean. So if we now subtract 160 from both sides, we're going to get negative 133.515 is equal to the opposite of the mean, which means the mean is 133.5 seconds. So there we go. We have the answer. The times it takes the Michelin Man to change tires is normally distributed. Tires are normally distributed with a mean of 133.5 seconds and a standard deviation of 16.1 seconds. And at the end of the day, when it comes to Mike Tyson cleaning clocks or the Michelin Man changing tires, which one is more exhausted? Oh, that's right, the Michelin Man. He's tired. All right, thank you and good luck.